you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, Mr. T here with a calculus tutorial. This is part 2 of our series on definite integrals and finding the area under the curve. In this part we'll be discussing these topics as I mentioned at the end of the last video. So from the last video, remember, using the fundamental theorem of calculus and the definition of definite integrals, we can find the area under a curve by taking the definite integral of our bounding function and our lower and upper limits, and we would then find the antiderivative of this, which would be x squared over 2, and evaluate from 3 to negative 3. Now we plug in our upper limit minus our lower limit being plugged in. So we get 9/2 minus 9/2 or 0. And that doesn't really make sense, having a 0 area. So I must have made a mistake here, and let's go back and talk about that mistake. If you remember from our definition, the definition that we gave, that I used in the last solution, was that f of x had to be entirely non-negative. It had to be above the x-axis. So if we graph our function here, y equals x, in our interval, we can see clearly here that that's not the case. F of x is below the x-axis on this side and above here. So let's just look at what would happen if we calculated the area of this left side here. So if we set up our integral going from negative 3, this is negative 3 here, and 0, and we'll find the area of this here. We get, when we plug in and do the same calculation, we get negative 9/2 for our definite integral. Now area should only be positive values, so a negative doesn't really make sense for area. But one of the things we just discovered here is that if we take the definite integral of a function that is below the x-axis, we're going to get a negative number. So we have to account for that when we go to solve area problems. Now the reason we got 0 in the last problem is I picked these two parts to be symmetrical, so our definite integral for this part was negative 9/2, and the definite integral for this part is positive 9/2, and if we add those together we get 0. So that's where we got 0 on the last problem. So for area problems, since negative does not make sense, we need to break our interval into subintervals such that in each interval the function is either above or below the x-axis. We'll find the area of each of those separately, and when we get a negative answer, meaning that the function had been below the x-axis, we're going to take its absolute value, and then we'll just sum up all of those parts. So if we relook at our example and do it the correct way here, we would have to divide this into two subintervals. So here we're going from negative 3 to 0 would be our first interval. And our second interval is going from 0 to 3. You can see here that I've taken the definite integral of each part separately, and I've put absolute values here just to make sure if it happens to come out negative, we'll take the absolute value. If it happens to come out positive, the absolute value of a positive number is still positive, and show the work here of doing our definite integral by hand. And we get again negative 9/2 for this part, which we had found earlier, and take its absolute value, do the same for this part, and now we have to add those two together. So our correct answer for this simple problem that we had would be an area of 9 square units. Now, if we are using a graphing utility to find our areas, we can make this even easier by the fact that if we take the absolute value of a function in the graphing calculator and graph it, it will reflect the areas that are below the x-axis and flip them over to be above the x-axis. But the areas that we're interested in, the area of that flip part, will be the same as the area below. So by taking the absolute value, we'll be creating a new function that is completely non-negative, meaning it's above the x-axis everywhere, and we can just take a single integral. So let's look at an example with that. So I've first shown the work here to do it in the formal or the manual method. So this is our function with the x-axis, and we're given this interval. So by looking at this function, if we factor it into a difference of two squares here, whoops, that's 1, and set that equal to 0 to find our x-intercepts, we get x-intercepts of -1 and +1. Now this -1 is not in our interval, but we have a x-intercept between this interval. So we need to split this up into two intervals, from 0 to 1, and then from 1 to 3. And we will take the area by taking the absolute value of each of those definite integrals. So I've shown that here, setting that up here. The integral of x squared minus 1 is x cubed over 3 minus x. And we have to evaluate that from 1 to 0 and from 3 to 1. So we substitute in our upper limit and our lower limit and subtract those numbers, and do that for the second integral, or the second definite integral. Here we get -2/3, and we're taking the absolute value, which is going to be +2/3. And here we get 6 minus a -2/3, which is 6 2/3. Its absolute value is still 6 2/3, and when we add those two numbers together, we get 22/3. So let's look at that in the graphing calculator. So let me clear this out. So let's enter our function. Now I'm going to enter the absolute value. Remember, to get the absolute value, we'll press the math button and go over to the number menu and select absolute value. And now we want to take our function here was x squared minus 1. And we can graph that. Now we would know this would be a parabola with a vertex at 0, -1. But when we graph it here, it reflects that part that was under the x-axis up here. And now we can take we have it being entirely non-negative, so we can take our area here by taking second calc 7 and go from 0 to 3. Now our answer is slightly different than the exact answer, and that has to do with the way the graphing calculator determines these. The graphing calculator is not computing this antiderivative and substituting in. It is using those Riemann sums that we talked about before. It's dividing this up into lots of very tiny rectangles and adding them up. And sometimes on some areas we get a small amount of error. And this time it seems like this had to do a little bit possibly with our absolute value here. If I did a little experiment, if I took the area of each of these parts separately, let's just look at this. Let's go from 0 to 1. I get my 2/3 here, and if I go from 1 to 3, I hit the wrong button here, obviously, so let's try again. We You can see here we get the 6 2/3 that we got, and if we added those together we would get the exact value. So you have to be a little careful if we're working a problem where we need to have the exact value. It might be safest to integrate these in each of the individual pieces. But to get accurate enough answers most of the time, we can take this shortcut that I just showed you. So let's look at one last situation here. And on this problem, we're not given an interval. We're not given the left and right bounds. It's asking us to find the area of a closed region. So let's graph this function so we can talk about what I mean by that closed region. So let's go back to our y equals here and type in our function. 3x cubed minus x squared minus 10x, and let's graph that. Now we're bounded by this function and the x-axis, so the closed region is this bump here. So it's closed in, and here's closed in. Up here, that's not closed in because it goes up to infinity. Over here, it's not enclosed. It's not enclosed here, not enclosed in these areas. So we have this area here. Now, since part of it's above and part below the x-axis, we want to use the absolute value. And we also have to find our bounds for our left and right. So that will be our x-intercept. So we can see here on the right side, our right bound is going to be 2. On the left bound, it looks like it's a decimal here, so let's find our x-intercept. So we can go use the calc menu here for finding zeros. And I need to move my cursor over here. You should know how to find x-intercepts using your graphing calculator. And it looks like we get here negative 1 2/3. So this will be the left and right bound. So we're going to be integrating from negative 1 2/3 up to 2 of our function here. And since it's partly above and below, we're going to be taking the absolute value of that function. Now I could re-enter with the absolute value, but I'm going to enter a second function and use what's called the vars function here. So let's bring up our absolute value first. And I just want to reference this y1. So to do that, I can press the vars button, move over to y variables, and it's a function, and I want y1. So when it calculates this second function, it's referring to that formula. So let's press graph. That's a little confusing on the screen. We've got two functions. We've got our original function, and then we've got the absolute value. So when we go to take our area using our definite integral here, if you've got more than one function in your graphing calculator, up on the top here will define which function the calculation menu is working with. And to toggle between functions, we use these up and down arrows. So I want to make sure I'm dealing with y2 because that's what I want to integrate here. Now I enter my lower limit, which was negative 1 2/3. We could enter this as negative 5/3. And now we can enter our upper limit, which was 2. Now we'll know that we had the right function here because it's not shading any of the area below that we had down here in our original function. And we get an area of approximately, if I round it here to say 2 decimal places, 17.23. So that's our area. It would be square units. So in this tutorial, we've summarized some special items that we have to do to take care of the fact if the function is below the x-axis because we get negative definite integrals. So we're using the absolute value function of our calculator to handle that situation. And also in our last example, if you are not given explicit left and right bounds and you're told to find the area of a closed region, you'll be finding the x-intercepts of the function to find your closed interval. So I hope you have good luck handling these more complicated problems, and talk to you later.
Are you ready? Are you ready?